Hi, this is Xiaoyang Mao, and currently I'm a professor at the University of Yamanashi, Japan. I would like to take this opportunity to say a few words to express my condolences to Professor Kuni, who was my PhD supervisor. I think I was very lucky to be able to pursue my master and PhD degree with Professor Kuni during 1985 to 1990. I think what I learned from Professor Cooney is not only the knowledge of computer graphics, but more the attitude toward the research. I remember Professor Cooney always said that as a researcher, you have to set out from requirements. Any research must have a need from society. At that time, Cooney Lab has collaborations with people from various fields. I have been involved in the project with a doctor trying to build 3D functional map of rat brain from cross-sectional images. And it was my great honor to be able to publish my first paper about the project on the Visual Computer Journal in 1986. In the past 30 years, I've been trying to practice what I learned from Professor Cooney in my research career and also trying to hand it to my students. Recently, I'm working with eye doctors trying to use image processing and augmented reality technology to support people with visual deficiency. Now, I would like to introduce my PhD student, Zhenyang Zhu, to deliver the talk about our work for helping people with color vision deficiency. So Zhenyang, please.
Thank you for Professor Mao. Hello, everyone. I'm Zhenyang Zhu from University of Yamanashi. Regarding to CGI 2021, our paper, Image Recoloring for Color Vision Deficiency Composition, a survey, was accepted. But please allow me to introduce my doctoral research, which is related to our survey paper. The title of my presentation is Personal Degree Adaptive Image Recoloring for Color Vision Deficiency Composition. Its contents of today's presentation. Its overview of my research. First, I will give a brief introduction about CV and color vision deficiency and existing studies contained in our survey paper. Then I will introduce our concept of recoloring model. Next, according to CVD simulation models and the composition targets, we propose 4 recoloring algorithms, that is OptLMS, OptLAB, FastRem, and PER-IR. Finally, we conducted evaluation experiments to validate the effectiveness of the proposed methods. CVD, which is short for color vision deficiency, is one kind of eye disease, and it is known as color blindness and color weakness. Dichromacy and anomalous trichromacy are common types of CVD. People with CVD may experience loss of color contrast. For this example, individuals with dichromacy cannot distinguish the red flower and the green leaves. Color perception is related to 3 kinds of cone cells, such as L, M, and S cones. These cones are sensitive to red, green, and blue light. If one of these cone cells gets disordered, dichromacy or anomalous trichromacy occurs. This survey introduced 2 CVD simulation models. In dichromacy simulation model, a color gamut of dichromacy is defined as 2 half-planes in the LMS color space. Colors in the 3D space are projected onto the half-planes for dichromacy simulation. Machado adopted a theory that CVD is related to the shift of cone sensitivity curves, and the gamut of anomalous trichromacy is subspace of the 3D gamut. The degree of CVD is determined by the amount of shift. The second row shows the color gamut of varying CVD degrees. The gamut of CVD is shown in gray. With the increasing of curve shift, the gamut becomes smaller. This is an example of simulation result for different CVD degrees. When the curve shift increases, loss of contrast becomes severe. In our survey paper, existing recoloring algorithms were classified into categories of dichromacy and anomalous trichromacy. These two tables in our paper summarized the methodology and experiments conducted in the existing studies. Please refer to the paper for detail. This survey also summarized evaluation metrics in the existing study. For example, image scoring metrics require CVD participants to score recorded image according to their subjective impressions. Please refer to our paper for details. Our study aims to use image recoloring approach to compensate for color contrast loss caused by CVD. The two key tasks of this study are to simultaneously enhance contrast and preserve naturalness and adapt the recoloring to CVD individuals. Contrast can be defined as the distance between colors. In this diagram, the distance between Ci and Cj is defined as the contrast of two colors. If these two colors are projected into the CVD gamut, the distance are shortened and the color contrast loss occurs. To enhance the contrast perceived by CVD users, we enlarge their distance within the CVD gamut. However, the original image without any process is supposed to be the most natural to CVD users. For this case, tilde Ci and tilde Cj seen by CVD users are most natural. For contrast enhancement, the distance between two colors is enlarged, while their distance to the origins are also enlarged. As a result, naturalness loss occurs. This is a recurring result of Machad's method. It does not consider naturalness preservation. As a result, it may recolor blue sky to gray and cause loss of naturalness. For naturalness preservation, the distance to the origin should be minimized. In our study, we aim to accomplish the task one, that is, simultaneously enhancing contrast and preserving naturalness using an optimization model, which considers contrast enhancement and naturalness preservation. For dichromacy composition, our first model was proposed in LMS color space. Given two colors, Ci and Cj in the 3D LMS color space, if they are projected onto the gamut of dichromacy, then CVD simulation colors CIS and CJS are obtained. Because the distance between CIS and CJS is shorter than that between Ci and Cj, and then contrast loss occurs. The proposed method optimizes colors for enhancing contrast in the gamut of CVD while preserving naturalness. Finally, the optimized colors are moved back to the 3D space and shown to CVD users. Because LMA space has no perceptual uniformity, then we propose to record images in the CIE-LB space. In the LAB space, the gamut of dichromacy is defined as dichromatic plane pi in the existing study. Similar to our first method, we project all color onto the dichromatic plane and perform optimization in the plane. This is an example of the coloring result by LMS and LAB method. The contrast between the sun and sky in the recolored image is enhanced and the naturalness is preserved. However, these two methods are time-consuming, so algorithm acceleration is necessary. CVD simulation can be thought as to map CVD maps colors to the CVD gamut. We propose a fast remapping method which remaps colors to the CVD gamut using a linear projection matrix of F prime. The coefficients in the 3 multiplied 3 matrix is obtained using an optimization model considering contrast and naturalness. This is an example of recoloring result by 3 proposed methods. FastRem obtained comparable effects with LMS and LAB method, but the computation time is extremely short. On the other hand, these methods are all for dichromacy composition, and their effects for individuals with varying CVD degrees is limited. To adopt our recoloring model to CVD individuals, we adopt anomalous chiromacy simulation model and perform the optimization within the gamut of anomalous chiromacy. This is an example of the recoloring result for individuals with varying CVD degrees. For each CVD degree, the recolored image by the proposed method provides sufficient contrast and preserved naturalness as much as possible. To evaluate the effectiveness of the proposed method, objective and subjective experiments are conducted. Please refer to the paper for details. Again, this is the overview of my research. Thank you for your attention.